So this is a collaboration between scientists at NOAA and us. So because geostationary is mainly NOAA purview. So it's not we don't really do a lot of geostationary, at least we haven't done in the past. We built a team actually that is quite extensive. You know, we have people from different NASA centers, Ames, Goddard, and Marshall, and then we have folks from NOAA and from Japan and Korea, because everybody's trying to get into geostationary now. So, and we wanted to work with them as much as we can. And we have some people who have extensive experience with EOS products and things. So these are the topics that I'm going to cover. So why this particular time is so critical? Because there is a generational shift in geostationary satellites in terms of their capabilities and what they offer, especially for land monitoring. As you know, geostationary satellites were mainly designed to support weather operations. So they were never really intended for land surface monitoring and all. But now I think that is changing. And along with the new capabilities, they also produce a lot of data. And we think what we built in terms of NEX and openNEX are really ideal for processing those new observations. And GEONEX is the pipeline that we built to take the geostationary data and turn that into products, just like EOS products that we've been doing for the last 20 years. And this is the guidance that we had from headquarters, not to do any new products, new algorithms. So this is something that we took to heart, and we basically took most of the algorithms from either the operating system or what NOAA has already done before. So we're kind of taking the best of both programs. This is GOSAR and this is EOS. And so in the last year, especially, we have done some preliminary work and produced some products that I'm going to talk about. And then I'm going to talk about how we're engaging the community in different ways. Okay, so when I say a generational shift, and this is what I'm talking about. So this is a GOES 13, and then the new generation GOES 16. So we're talking about 3 times more channels. So GOES 13 has 5 channels, and 16 has 16 channels. And the 16 has some bands at 500 mid resolution. So it's almost like 4 times better resolution now than we had before. And faster scan rates. So now we have full disk every 15 minutes, continental US every 5 minutes, and then we can take snapshots of selected areas 30 seconds. So we have amazing capabilities actually with this new generation GOES satellites. Okay, so but we also think that a lot of the band selection that went into these new generation actually is quite similar to, especially for land monitoring, to what we have for MODIS and VIIRS. So these two are our workhorses for the EOS program. So a lot of the algorithms, both land, atmosphere, and oceans, they were designed based on the specs off of MODIS and VIIRS. And if you look at these different geostationary sensors, this is the list of sensors that is either up or going up in the near future. So ABI, this is GOES-R program. AHI is Himawari, this is the Japanese. AMI is the Koreans, they have their own series that are planned. And then FCI is this Meteosat European program. And AGRI is the Chinese Fengyun series satellite. So these are the sensors that we'll have access to in the near future. And you can see all of them have very similar configurations. There are some missing bands that we don't see, and there are also minor differences between each of these among these geostationary sensors. But overall, they seem to capture the spectrum that we're interested in for land monitoring. Okay, so this is the spatial coverage. Once we have all these assets up in space, so right now we have Himawari in there, and the FY4 is there, and 16 and 17 are there. And then this is the Meteosat 3rd generation. So I think their launch date is about 2021. So right now we have this part covered with the specs that I'm talking about. and this part covered already, with what we have. And with the current configuration, we get about 1 to 2 kilometers, 5 to 15 minute interval. So we're talking about pretty serious coverage, But the problem with these geostationary satellites, they're really designed for weather. So they focus more on the coastal areas. So you can see the Midwest and all, they have poorer coverage relative to the polar orbiters. Okay, so we already know that the ghosts are actually already, contributed significantly to the weather forecasting, because we never had this type of imagery before. You can, with real time, you can see, how the storms are moving, and then, when they're going to make landfall and things like that. But what does it mean for land? Is our primary interest. So, as you know, when you stare at a landscape, you are bound to get more cloud-free observations. That's what we see here. So this is a 16-day MODIS composite, of Himawari coverage area, and over the same 16 days, this is what you get from Himawari. So there's a significantly more cloud-free observations compared to the polar orbiters. So in a single day, we get more clear sky observations than 16 days of MODIS data. So over a 16-day period, you're getting almost 90-95% cloud-free observations. So that is really the key to working on the geostationary, because you are actually beating the cloud cover, and some of these areas are perennially cloud covered. So with the polar orbiters, it's really difficult to get through the clouds. And that's one advantage that we have with these. But now that we have all these observations, that we never had before, so this is what, to me, the geostationary contributes, is the diurnal processes that we never had. Even when we had 2 MODIS sensors and VIIRS, still we have only snapshots. Like VIIRS and MODIS, they're around 1:30 and 2:30 in the afternoon, and then Terra MODIS is at 10:30. But so you're getting 3 shots. Compared to now, we're talking about every 5 minutes, or every 15 minutes. So this is an example of what we can do now. So this is a land surface temperature image from Himawari, looking at Australia. So this is, I think this is Adelaide, Australia. So they had a heat wave in January of this year. So we're talking about temperatures that are 55 degrees Celsius. For a few hours, they could not even drive on the paved roads because they just couldn't. Yeah. So, but again, we never had this ability to actually watch the heat wave in real time. How it is actually coming from the interior of the continent down to the coast and then going back. This is another example of fires in Montana. This is last year, and it was one of their worst years of fires. You can see how many fires are burning simultaneously.
Wow.
Yeah. So again, that kind of synoptic view of the continent every 5 minutes. So we never had that option before. This is another example. And I never thought I would see this. This is a diurnal snow dynamics. So watch this area. This is Wyoming, and this is Laramie County in Wyoming. And see what happens in a single day. So starting about 7 o'clock, you can see, snow kind of melts completely in a matter of 4 hours. Oh, here, right here.
Okay.
Yeah, and then you see snow disappearing in a matter of a few hours. 5 minute is actually a given for the U.S. Okay, so this is another example of what we can do now. As we all know, from our energy and balance observations, that when you have contrasting surfaces next to each other, you kind of create these local circulation. Okay, so let's say people have studied forest versus ag land, where a forest would have a lower boundary layer compared to a cropland. So that creates this local circulation, and then that's how we generate the storms and then the precipitation in the afternoon. So that's a typical thing that we have known, but we never had the observations to support those things before. But now we do. So with this the geostationary data, we can see how. So this spectral window difference is the difference between two channels. I think it's centered around 10 and 12. So it's the difference between those two channels that gives you the height of the boundary layer and how the boundary layer is actually established at any given time. So this, you can see this is the forest area, and this is the savanna. So they're right next to each other, but their boundary layers are quite different, from each other. So that sets up the circulation pattern. So ultimately resulting in clouds and things like that. But now we have this ability to watch it in real time, how those dynamics are changing over the landscape. And then if you go here, this is the other ability of the GOES satellite, where we have cloud, but we also have a lightning mapper, that on board, the satellite, so you can see the storms develop and actually move, from the area that we're talking about. So there are actually quite a few capabilities, for this sensor, and then we have all this data coming into the system. There are so many things you can do, and I don't even know how we actually generate these products and then engage the community, because I don't even know how to handle 5-minute data, really. Yeah. So it has to be something that you can do on demand. So I see something happening in my area. Can I actually launch a process and then do this? Because you don't want to compute all these things all the time. Really, then you're going to fill up petabytes of storage. So this is a challenge that we have. We have to think about how to navigate this area, because this is kind of new. We never had this before. Okay, so we're looking at about 3 terabytes per day. Is a raw data that we're looking at. From our own geostationary, and then the Himawari, and then maybe the Chinese, if we let if we can access their data, and then ultimately the Europeans. So the raw data itself would be about 3 terabytes. So that's the full disk data that we're talking about. So and then we don't really have anywhere except NEX, that where we can actually ingest and process some of this data. So so we're approaching this whole project in 2 different ways. One is real time, so where we have to process the data as it comes. Okay, because some of the things like fire and stuff like that, we don't want to go into an archive, because those are all real time monitoring things. So all the stuff is done on the cloud under the openNEX, that we built with open access. Okay, and all the standard products that we're talking about, whether it is aerosols or photosynthesis, all that stuff will be done on NEX that is available to the community, more as a typical DAC that we're talking about. But without this infrastructure already in place, probably I would have never touched the geostation. Okay, so this is the current configuration of what we have. So we have like I said, the near real-time products that are mainly generated on AWS. Because NOAA already has an agreement with AWS, where they dump all the data onto the cloud, and then we run our algorithms, and then finally they end up on the world view with the data at some point. This is the pipeline that we're building right now, and I'll show you some examples. And this is more of a standard process where data comes from Marshall. They have two dishes, one for goes east and one for the west. And then we get the data, and then we also get the data from Chiba University for the Himawari. So once we have all that, we grid those data into these 600 by 600 kilometer grids. But once we have these, and then we have a standard processing that we have typical EOS type, brightness, temperatures, surface reflectances onto other products. And all of them will be available permanently on NEX. So that's one good thing about the way we set it up, because I cannot imagine folks going to a NOAA archival center, that they built. I think it's called so class system. Take forever to actually download. One day of data probably will take you one day.
It's real time.
That's what we're building, because we have a pretty good archival system. We have the tape system is kind of unlimited, so we can dump as much data as we want into the tape system.
So the raw.
Okay, so these are the products that we have plans right now. So you may recognize a lot of these. These are typical EOS products. Surface reflectances, fire, VIs, LAI, FR, surface temperature. So these are all products that people, the community has demanded over the years. So, and we're going to basically, try to produce all of them using different algorithms. Some of them are already working with MODIS and VIIRS. Some of them are working with GOES API. So there are different implementations, that we are trying to take and then integrate them in the pipeline. Some of them we prototyped already, some of them we're working on. So we're in different stages of producing these products. And as you can see, again, these are all 1 kilometer, majority of them daily. So we're talking about a lot of data at the end of the day. Okay, so these are some of the examples of what we've been doing. This is what is going to be. We are running a NOAA algorithm for fire detections now on the cloud. So and you'll see something like this when we have these 5-minute. So it will take us about 2.5 minutes. So every 5-minute acquisition, we take about 2.5 minutes to process.
Is that
the 5-minute comes, I think it's maybe about 100 seconds, I think, from the time it is collected at the satellite, and by the time it ends up on the cloud is about 100 seconds.
Because you can see
because this is a color composite, so yeah, it is obscured. Normally, when you do only fire detection, you won't see the smoke and all. You just see the fire.
The thermal, right? It would be a thermal.
Okay, so these are other products. So this algorithm is widely used in EOS. This is a multi-angle implementation of atmospheric correction. This is something like a 6S code that is widely used for producing surface reflectance from the top of the atmosphere. So this algorithm is from Goddard. One of our colleagues works on this. And then we took that, we implemented it first for Himawari, and it actually works quite well, compared to what we have done with MODIS. So this, again, is an example of what we do when we run this code over multiple time steps. Okay, here, we're tracking these controlled burns in Australia. So with the Himawari, you can actually see those aerosol plumes that you can watch as the smoke spreads. Okay, so this is another example of what our colleagues are doing in Japan. Again, looking at clouds and solar radiation, and then actually forecasting those vectors out into the future, so that the photovoltaic energy can actually plan on what kind of an output they can count on based on, again, and this is based on Himawari data. Okay, these are typical VI, vegetation indices. Again, this is the same area of Himawari, but the thing that we want to emphasize is that we have changing sun angles and changing view angles within the footprint of the geostationary. So you have to account for the angular effects of the observation. So, and this is a fit of the directional reflectance. So what we're saying is the raw data probably is not that appropriate, as we all know, that, unless you normalize for the geometry, and you may not be able to use it in a standard way. So, but this we already do this in EOS, so we're trying to implement it for this data set. Okay, and then on to downstream products. This is an example of leaf area index and a fraction of absorbed radiation. Again, a function of how much vegetation is there on the ground. And when we compare the MODIS versus Himawari, we're making progress. We're not there yet because we still have to tune the lookup tables because they have slightly different characteristics in terms of wavelength, width, and then the angles and things like that. So, but we're making progress on that. So we work with Boston University on this one, and this is something that new that we started. This is work that colleague Hirofumi has been leading. So one of the things that we wanted to do with the geostationary is, even though we get the clouds and surface temperatures and all, but there are a lot of other data that we need. So we need surface observations on precipitation, humidity, and we have observations on snow. So we have a lot of observations that are available, but we're not taking into account in real time, in near real time. So now we have, brought all these data into our simulation system. So we have maybe a couple of thousand surface observation stations and a few thousand SNOTEL. They all come in within 30 minutes, into the system, and then they get integrated. He's using more of a random forest in a machine learning algorithm. And then every hour we produce these fields, at 1 kilometer. Precipitation, temperature, humidity, and solar radiation. So every hour, within 30 minutes after the hour, so we have this data available, not only for us, but for the whole country. And I think right now, actually, this reading system, we beat everybody else by about 30 minutes, including NOAA, actually. Okay, so once we have that data of driving variables, and we already have the FBAR and NDVI and all that from satellites, so now we can do almost real time in a carbon exchange. Okay, so we have radiation, we have the state of the vegetation. We can compute actually, what the landscape is doing in terms of carbon absorption. Okay, so this is hourly. But once we have this ability, now we're talking about how we can integrate this with other sensors like OCO2 and GeoCarb, because they're also giving something very similar, in terms of carbon exchange. So now, but these, GeoCarb probably will have regular observations just like these. But OCO2 is a typical polar orbiter. They don't have many observations, and many times clouds obscure these observations. So, but now we can actually use wherever we have those, tune the models, because we know that OCO, is actually quite strongly related to the observed for the GPP. So whenever we have these observations, and we can actually tune and then test, how well we're doing. So it's almost continuously we can update the models. Okay, so this is one of the things that we're doing to engage the community. As you know, this is a lot of data, so obviously not everybody's interested in downloading all the data. So we kind of concentrated on 4 different regions. And then we're creating these data sets that are co-located with MODIS data. Because that's what most people want to do, is, they want to do something that, and then compare with MODIS data, because, MODIS is the gold standard right now. And so what we did was, we created these co-located data sets, and then people can download them and then do their analysis.
Why not Europe?
Europe, the problem, Europe, so they were ahead of us, in terms of their 2nd generation geostationary, but they are not as good as us, So now we are ahead of them. So the MSG is, I think their best resolution is 3 kilometers. So in the beginning, when they first launched MSG, so people were excited about it, but very quickly, 3 kilometers wasn't really cutting it, because we have MODIS, with 1 kilometer. So the whole community kind of moved away from it. So I think until they launch their MDT, so we're going to be leaving that part. Okay, we also have a special issue that we're running. This is open general remote sensing, and so people are encouraged to use some of the data that we're putting out and do the analysis and write papers. But if they're willing to share the codes that they used, so we are also going to make them available on our system. Okay, so this is where we're going. This is 2023 when I'm going to retire. But this is the plan, for GEONEX. So what we want is it's going to be completely deployed on the cloud. So I think NASA Sense already made the decision to move to the cloud. So I think in 5 years probably they'll be there, and we want to be there first. So and on-demand processing. And so we're thinking, instead of doing this regular processing and archiving, and so we want to see whether on-demand processing is actually economical. Okay, and the conversational assistance. So that's an area that we are working on in a big way. So we have our own project developing a capability called MATA. So actually today is the first day that I found out that NASA is actually filing a provisional patent for this. And so basically, MATA allows access to all their science data, more on a conversational basis. So you can actually query, all the data that we have. So what we're doing is, so we're developing different skills, So now things like Alexa, Siri, and all what they call the skills, So skills can be in different areas, controlling light or air conditioner. Home control is a skill, for example. So in the same way, we're developing skills where people can interact with geospatial data. Okay. So you should be able to ask, for example, Alexa. So you have to invoke Alexa, say, Alexa, ask Martha, how much rain did we get at Moffett Field in the last hour? So you should be able to give you an answer, that we got 5 millimeters of rain. So that's where we're going. So you can ask, are there any fires, in the vicinity? If there are, how far are they? So things like that. So that's what this whole infrastructure in the end is actually is designed to support these, these types of interactions. So as you can see, we're kind of moving away from standard science products into more operational and decision making. Okay, so this is the summary. Basically, there's a lot of potential to study diurnal variations that we never had the opportunity in the past. Think about it. In the past, we used to fly airplanes several times over a landscape to see how it is changing. But now we have these observations anywhere you want, and this whole area for near real-time disaster monitoring that we never had again that kind of opportunity before. And this data model integration, it's the same way. We have been using MODIS and VIIRS, all this data, mainly to look at internal variations. So seasonal to internal variations. That's how we used to tune the models, whether you're getting the dynamics or not. But now we're talking about actually tuning the models on a diurnal timescale. Whether you're actually producing the type of bundle layer, on dynamics that you expect. But we can actually validate with the data that we have. So, and from states to fluxes, the last 35 years, I spent mostly on mapping the state. So, is there snow, is there vegetation, is there water? But now we're talking about what are those states doing? Are they actually exchanging, mass, energy, and things like that? So, so that's a huge, advancement with the geostationary. And this whole GeoLeo, we spend a lot of money in designing and launching polar orbiters. We have a lot of experience and a lot of knowledge in terms of processing the data and in calibration and then retrieving different parameters from the data. But now we can apply all that knowledge to geostationary data. So that combination of GeoLeo, I think is going to revolutionize in the next 20 years. But all this, obviously we cannot fund, all this. So that's where the community and engagement comes in my view. So already all the hooks are in place because with the geostationary, all the data will end up on the cloud. So we are already there. NASA, NOAA already has an agreement with AWS, and they have an agreement with Google and Microsoft. So all the companies basically are hosting the data right now for free. Okay, we'll see what happens in terms of the economics of it, but they are hosting it for free and making it available on the cloud. So that allows us to do rapid prototyping that we never had the option before, and low latency data production, and ready to deploy containers. So again, we have so much knowledge, between Himawari, between MODIS, and all those are slowly being containerized. If you go to like Google Earth Engine, there is a lot of knowledge actually that is already containerized. So we should be able to take some of that knowledge and then build off of that using the geostationary data. So not having to wait at the next cloud-free MODIS data, we know with using geostationary, you're more likely to get a cloud-free shot. Finally, this whole data-driven, we have not gotten into it yet, but we think having this high-frequency data allows you to build these machine learning models that we were never able to do. Look at the fire behavior, for example. If you can learn from those events, that under what conditions you can expect a certain behavior, I think it'll be incredible. So I'll stop there and answer questions.